Hello students, and welcome to a new lesson in A-Level Geography where we're going to be looking at all the skills you need in order to do the A-Level Geography skills paper. We'll begin by looking at graphs. Firstly, we'll look at a semi-logarithmic graph. Now this is a line graph where one axis is going to increase at an arithmetic rate, so for example it may go up as 1, 2, 3, 4, 5, but the other rises at a logarithmic rate, so it may go from 1, 10, 100, 1000, 10,000. So it looks kind of like this. On our x-axis we have the standard of living, which is moving up at an arithmetic rate, 0, 1, 2, 3, 4, 5. And on the y-axis we have the size of the population, which is expanding at a logarithmic rate. So we're going up from 0.1, 1, 10, 100, 100,000, etc. And this is measured as the size of the population in thousands. So it's pretty much really simple to plot. It's just like a line graph or a scatter graph. So all you have to do is plot on all of your points along it, and then draw a line of best fit or connect up the dots depending on what the question is really asking you in order to plot your semi-logarithmic graph. Now we're going to look at a divergent bar graph. This is a bar graph to show both negative and positive values, so it looks somewhat like this. On our x-axis we have the countries, so we have China, the UK, USA and Spain, and on our y-axis we have the population growth in thousands. As you can see, we can see a negative value such as that as China, who is experiencing -3 population growth in thousands, and USA -1, and UK and Spain both show positive population growth. Population pyramids. This is a form of a bar graph that shows demographic makeup of a population, and it looks like this. On our x-axis we have a bar that shows the population in millions, and then we have bars stretching out at either side of a middle where we can see the population in millions of both the male and the female population. Then we have a bunch of age ranges which are going to show what each value of the bar, which is moving out horizontally, equals. So for example, if we look at that 0 to 4 at the beginning, we can see that there is approximately 1.5 million 0 to 4 year olds that are female and 3 million 0.4 year olds that are male. So then we can move up the bar and see the kind of general population levels of each of the age ranges. Now we're going to look at a proportional divided circle. This is a way to show totals and a component parts of a set of data. So here we have two they're in the form of pie graphs, but they can also be seen as proportional divided circles. On the left we have the type of energies that are used in Norway, and this is pretty much adds up to the equivalent of 3,400 tons of oil. Then on the right we have the energy used in Poland, and in total all the energy used adds up to 2,456 tons of oil equivalent. So we can also calculate its radius by taking the square root of its total value. So for Norway we take the square root of 3,400, which gives us 58.3. Then this will give us a radius of 5.8 centimeters. Poland, we take the square root of 2,456, which will give us 50, and therefore its radius will be 5.0 centimeters. They may ask you to do this in the exam, so don't measure it with your ruler and instead take the square root. Now we're going to see how they can be used as this proportional symbol. We can compare the sizes of them by putting them up against a scale. So you may have a graph where you're going to have to plot the country and the energy used in tons. We can put Norway here and put a Poland right next to it, and then compare its size, and we can see its energy used in tons just by the size of what it really is. So it's a proportional symbol to how much energy is really being used in that country. Now we're going to look at triangular graphs. These are graphs, they're kind of like graphs, they're similar, but they're meant to show three sets of data, and they look something like this. We have a triangle with a bunch of kind of coordinates which we can plot on, and three different axes. The first of which is going to be running along from the top to the bottom right, and this is going to show the percentage of nuclear energy being used. The bottom axis, which runs from the bottom right hand side to the bottom left hand side, shows the percentage of oil being used, and the percentage of hydroelectric power is shown by running from the bottom left to the top of the graph. Now we're going to have to plot points on this to show how much nuclear, oil and hydroelectric power is being used in a country. So first let's go and try and plot Brazil. It says that it uses 30% of its total energy is from nuclear, 8% comes from oil, and 62% comes from hydroelectric power. So how do we plot it on? Well, it's quite simple. Firstly, we have to move clockwise from each face and see where we're going to kind of draw from in order to plot each of our points. So the first face, which is the percentage of nuclear energy being used, is going to plot points looking down from the southwest side. So this is the side given where we're going to look downwards. You'll see what I mean by this in a minute, from southwest in order to plot points. The second face, we're going to look northwest and point our plots along the lines that way. And our final face is going to be plotting our points towards the east. So what this means is that we're going to have to plot a point here where it says 30% is going to be nuclear energy. So we're moving down the southwest direction of the lines. What this pretty much means is you can see here we have all of our values. We are then going to find a point. So since we're using 30% nuclear energy, we are over here and we're going to move southwest. So these lines which are going to come here, since our compass directions is north, then east, south and west. So we plot it along 30. Next up comes our next value, which is going to be 8% for oil. Since we're measuring from the northwest angle, we have all of our values here. We find where 8 would be, and then we're going to look at this up northwest. So we leave it here. And finally, we have our east-ended side, and we can see that 62% is hydroelectric power. So we find where 62 is and plot it here, and we're looking towards the east. So what this means is that we're going to draw our first arrow southwest coming down from this first point, our second arrow coming northwest from the second point, and our final arrow coming from the third point pointing towards east. Now you can see that over here all three of the arrows are going to cross. So this is the point in which we're going to plot our point for Brazil. And this is going to show the percentage of nuclear energy being used, which is 30, as we can see moving down from the southwest side. We can also see the percentage change with the percentage of oil being used, which is 8. If we look at North Sea, the percentage change of hydroelectric power being used. Okay, now you can have a go at plotting Canada onto the graph. Use the values here to see where it should be. Pause the video, plot it on, and then hit play whenever you're ready to see where it goes. This is where Canada would land. It is probably between, 50 and 60% hydroelectric power, 5% of nuclear energy, and 42% of oil, as you can see by moving up the northwest side, the southwest side, and the eastern side. Now we're going to look at radial diagrams. This is a diagram which shows the data which can be applied into different categories. So we have pretty much a big circle which looks like this, which is divided into sections. We can then assign each section a certain value. So in this case, we're going to be using the months. Now, we're probably going to be looking at the levels of river discharge in this graph and looking at how it does so in different types of months. So this is what you will pretty much get. You'll get a shape which shows the levels of discharge over time across each of these months. So how do we measure this? Well, each of the points here on this radial diagram are going to be assigned a certain value. I've drawn them on the side because there won't be enough room for me to put them there and be so clear. So this pretty much means that at this point here, at 0, we are going to be experiencing 0 Qmax. At the next point, we're going to be having 10 Qmax, and so on, so forth. So if we plot on a point here, so in January we had X Qmax, we are then literally going to have to find the value here, which is 30 Qmax. Now we're going to look at the storm hydrograph. We looked at this in our AS Physical Geography course, and it effectively shows the characteristics of a storm and the effects it has on river discharge. So these green bars here are going to show the levels of precipitation, and the other axes on the opposite end is going to show the levels of discharge, which is highlighted with the blue line. Then we have the hours of the rainstorm shown on the x-axis, which runs from 0 to 72. So as we can see, in the early hours of the rainstorm, the peak rainfall, the rainfall begins to increase, and then we have peak rainfall at our highest bar. Then it begins to decrease after peak rainfall. Now at peak rainfall, we start to get our lag time until the point here where we are going to get peak discharge. The time between peak rainfall and peak discharge is called the rising limb of discharge. Then when we lose peak discharge because there's going to be less rainfall, there is a receding limb where discharge then decreases, and the pattern will repeat itself again when there's another storm. Now we're going to look at the Hjulstrom curve. This is what the Hjulstrom curve is, and it shows how sediment is eroded, deposited, and also transported in a river. Here we have our average velocity, and then at the bottom we have our particle size, with examples of each particle here at the top. So we have two different curves. The yellow curve is the full velocity, and this is the velocity which it takes in order for the sediment to then be deposited. If it is greater than the average velocity is greater than the full velocity, we're going to be experiencing transportation. But if the velocity is less than the full velocity, we're going to be experiencing deposition. The same goes for the entrainment velocity. If we have a velocity higher than the entrainment velocity, then we are likely to get erosion. However, if it's lower, the sediment is only going to be entrained and transported. So we can call this the transport zone because it's above the full velocity, so it's not being deposited, and it is below the entrainment velocity, so it's not being eroded. If, like we've said, we have sediment below the full velocity line, we are experiencing deposition, and over the entrainment velocity, we are experiencing erosion. Now we're going to look at central tendency and also measures of dispersion, and we'll begin with the mean. So this is very straightforward. It's just the average of all of the results, and we do this by adding up all of the results we had and dividing them by the total amount of readings we took. The median is a middle value of all of our data. So what we do, we line up all of our results and then take away from each end until we repeatedly get to the middle, and that middle value is going to be the median. If we are left with two results, we have to add them together and divide by 2 to get a median. The mode is just the most frequently occurring result in our set of data. So for example, if this is our set of data, we are going to see that in fact there are 3 3s, which is a greater number than any other, and therefore the mode is 3. The range is the difference between the largest result that we gather and the smallest result in our set of data. We take away the smallest one from the largest one, so if our set of data is 8, 3, 6, 2, 4, 5 and 5, what we have to do is take a range of 6 because we subtract 2 from 8. Standard deviation. Standard deviation is a bit more complicated, and it's used to show how spread out data in a set of results is. So what's the standard deviation of 5, 7, 9, 12 and 19? First, we have to calculate the mean of the results. So in this case, the mean is 10.4 because we've added up all the numbers and divided by the amount of readings we took, which in this case is 5. We then subtract the mean from each reading and square that value. So we have to subtract 10.4 from 5 and then square that, which gives us 29.16, and repeat this for every single value, which you can see on screen now. Then we have to add all of these values together, and this equals 119.14. We then divide this by the total sample size, which in this case was 5 because we got 5 readings, and then we subtract 1. We then divide this by 4, and this gives us 29.75. So the reason we get 4 is because the sample size was 5, and we subtract 1 from the sample size, which gives us 4. So 119.14 divided by 4 is equal to 29.785. Then we have to square root this answer in order to get our standard deviation. Our standard deviation then results in being 5.48, which is quite deviant from the mean, which was 10.4. This is the equation which we use for standard deviation, which is pretty much shown up here. S stands for standard deviation's value, and this epsilon counts as the sum of x number of values, and x minus x, x is used for one of the values that we get, so for example 5, and we subtract this from x with this little dash up top, which means the mean of all the values. We then square this and divide it by n, the number of sites, divided by 1. Subtracted by 1, and then we take the square root of this as we've done, and then that gives us standard deviation. Now we're going to be looking at the interquartile range. The interquartile range, it begins with the upper quartile. How we find the upper quartile is by ranking the data from highest to the lowest reading. The upper quartile is the midpoint of the results, which is greater than the median. So to do this, we have to calculate n, which is the total amount of readings we have, plus 1 divided by 4. With this value, we find the results which lay between it. So, as we've said, n is the number of results, and let's say these are all the results that we get. We can rank these then from the largest to the smallest as a form of median. So we do 13, which is the total amount of readings we got, plus 1 divided by 4, which gives us 3.5. The 3.5 value lies between 98 and 78, because as we can see, the third rank is 3, and the fourth rank here is number 4, where we have 78. So we add 98 and 78 and divide that by 2, and this gives us 88. So our upper quartile is going to equal 88. The lower quartile is pretty much exactly the same, but however, it's going to be the midpoint of the lower end of the results from the median. So to do this, we calculate n plus 1 divided by 4, just as before. However, we have to multiply this by 3. And with that value, we can find the results which lay between it. So as always, we get our number of results, which is 13. We then add 1 to get 14, and then divide by 4. Then we have to multiply this by 3, and this gives us 10.5. The 10.5th value in our set of data lies between 24 and 19, so we add these two numbers together and divide by 2 in order to get 21.5. Therefore, our lower quartile in our results is 21.5. Now we're going to calculate the interquartile range. As we know, the range is just the highest value minus the lowest value, so we do the upper quartile minus the lower quartile. 88 minus 21.5 is equal to 66.5, so the interquartile range is equal to 66.5. Now we're going to look at box-and-whisker diagrams. These are diagrams which are going to show the spread of results which use the upper quartile, lower quartile and interquartile range. How we plot them is quite simple. Firstly, we're going to draw a line along which is going to represent our lowest result. So in this case, if our lowest result in our set of data is 5, we draw a line along 5. The next line is the second lowest line in the box-and-whisker diagram, which is representing the lower quartile. Then we draw the median as our next line, and our line after that is going to be the upper quartile. Then we connect these again with two lines in order to make this box-like feature, which is going to link the lower quartile, which is the second lowest line, the median, the one in between the two quartiles, and the upper quartile, which is the highest at the moment. Then we have to draw a line even higher than that to represent the highest value which we have got. So in this case, it's just above 45, and then what we do is that we draw a line in between all of them, and this gives us our box-and-whisker diagram, showing the lowest result, highest result, and interquartile range. Now we're going to look at Spearman's rank. Spearman's rank is used to see the correlation between ranked data. So here's an example of how we're going to use Spearman's rank. We're going to look at the correlation between the site number and the width of a river. So we've ranked our site numbers, but we have to take the largest value always in Spearman's rank and rank that as number 1. Here we take the site number 10 and give that number 1 and work our way down. So the largest value here, which is site 10, we then give the rank number 1 to. Then we have to do the same with the width of the river, and therefore we take 6, which is going to be the largest kind of variable, and rank that as number 1, and then keep on ranking all the way down to 4.5, which is the smallest value in our set of variables, which is then 10. We then have to find the difference between both of these rank. So it's literally the first rank minus the second rank, which is 0 for the first part, and for example, if we do 7 minus 5.5, we're going to get 1.5, and we keep subtracting all the way down. We then have to take this value and square it. So 1.5 squared is 2.25, and 0.5 squared is 0.25. And we have to keep on squaring these until we reach the very end. Then what we have to do is calculate the sum of d squared, d standing for difference. So the sum of all of the results that we have is going to give us 12.5. We then have to multiply this sum by 6, which is going to give us 75, as 12.5 times 6 is 75. Then we have to calculate the number of the ranks that we've collected. We then have to cube that and subtract the number of the ranks that we have actually collected. So that is 10 cubed, which will give us 1000, minus 10, which is 990. We then have to calculate the sum of all of the difference squared times 6, and this gives us and then we have to divide this by the 990, which we've just gotten, which you can see here is sum times 6 divided by n cubed minus n, and this gives us 0.075. However, we're not done there because we have to subtract that number from 1. So we do 1 minus 0.75, which will give us our Spearman's rank of 0.925. And that is what our Spearman's rank is. Now we're going to look at movement maps. Movement maps are pretty much going to show how one person moves from one area to another, and they're often used in migration. The first of which is a flow line, and this is showing the width of the line from one person moving from one place to another, and it's proportional to the quantity of movement happening. It also follows the actual route of the movement. So for example, we can see here that someone may be moving from Orlando in Florida all the way to New York, and we are seeing that it follows the actual route, so they may have been driving through these states. Also, it is proportional to the quantity of movement, so that is quite a thick line, so we could say that perhaps 10 people were moving in that route. Next, we're going to look at desire lines. Here, the width of the line is proportional to the quantity of movement, but however, it's drawn directly from the source to the host country. So this is what it looks like. Here, we're moving the same kind of way from Orlando over to New York, and the line is still proportional to the quantity of movement. However, we're moving straight and we're not following the route. Trip lines are going to not be proportional to the quantity of movement because each line is representing one person when they are migrating from one area to another. It's drawn directly from the source to the host country, or the source area to the host area, and it doesn't actually follow the route. So for example, here we see a lot of people moving to New York from different places, such as Florida, Washington and Texas, and each of them represents just one single person or one single entity moving there. Now we're going to be looking at different types of data. Qualitative data is information about qualities of an object or entity which can't be measured. So for example, how good your dinner was. How good your dinner was isn't able to be measured and it is quite arbitrary, so as a result we can't assign it a certain value and therefore measure it. Now the opposite to this is quantitative data, and this is information about an object or an entity which can measure quantities, so information could be associated with numbers. For example, the amount of calories you had in your dinner. If your dinner had many calories, then we could probably take away each part of your dinner, each individual item of food, calculate how many calories are in that item, add them together, and therefore we can get quantitative data, which isn't really based on opinion. Primary and secondary data. Primary data is data which has been personally collected firsthand by a researcher when conducting an investigation, and secondary data is data which is used by a researcher which has already been collected by another researcher in the past. So for example, if you're conducting information on a study on rivers, primary data is a data which you have found when you were investigating the river. For example, the width of it and the depth when you went personally with a tape measure and the yardstick to measure the depth and the width. And secondary data is data which you're going to be using which is being collected by someone else. So for example, if you're calculating a mean of your results and you use someone else's data to help calculate the mean with, that data is secondary data because it has been collected by another person. This has been the end of the lesson, which has covered the skills you need to know for your A-level geography skills exam. As always, thanks for watching, good luck in your exam, and if you need any more information on your A-level subjects, be sure to visit the channel or www.revisealevel.co.uk. Good luck, and I'll see you next time.